So this is lesson 6.1, which deals with the introduction to what we call trigonometric identities. For the rest of the unit, we are going to be working with identities. And I'm going to say a few things here to try to motivate you in terms of effort and the amount of work you put into this. This is going to be something that many students typically will struggle with. And one of the problems, I see it this way, one of the problems is students look at some of the questions, and even though they know what it is they need to do, they freeze. They just look at it and they go, I don't know what to do. And your teachers have always told you in math, I hope, well, you have to try something. And unfortunately, sometimes you're not told what that means. So on your desk is a sheet, and these are the things you have to try. And I don't want to go through them right now, but these are the specific things you have to try. And sometimes you're going to try one of them and it's not going to work. This is the level of math we're at. We're not learning that these are the steps you follow to solve this type of math problem. It doesn't work that way anymore. And those of you in my calculus class know that you have to try certain things, and sometimes it leads you to success and sometimes it doesn't. And I have an analogy that I've used for many years here. Imagine that you're watching a movie, and in the movie the character is waking up in a foreign country and they're lost. They don't know where they are. Something's happened. They're all of a sudden, maybe they've been kidnapped and released. They're on a road and they want to get home. Okay? They recognize that it's probably in Alberta and they want to get home to Wetaskiwin. Nothing good is going to happen if the person just stands there and shivers and starts whimpering. Okay? What the person has to do is start walking. And sometimes what's going to happen is they're going to walk down that road, and the road will get muddier, and it will get narrower, and you'll start to hear growls coming from the bush on both sides of the road. And the person would then say, well, maybe I've taken the wrong path, so they go back to the beginning and they try something different. They go in a different direction. And that's the analogy that I want you to keep in mind when you were working through much of the rest of this unit. You have to try something, and if the math gets really ugly, then you've made a wrong decision. That's all. You just have to go back to the beginning and try something else on this list. But you have to try things. So this section deals with 3 types of what we call trigonometric identities, and we're going to be working on these today and tomorrow. Okay, so today we're going to go through the lesson and get some practice for tomorrow, and then tomorrow we're going to just practice more and more and more with this stuff. We're going to be looking at, well, first of all, what an identity is, but then we're going to be verifying trigonometric identities, determining non-permissible values of trigonometric identities, and we'll also be, it's really important that we start off here actually with the difference between an equation and an identity. And that's where we're going to begin. As a warm-up, this is going to teach you what an identity is. Consider this equation. This thing that I'm going to highlight is an equation. Give me a minute, please. I want to bring back something. I've lost, there it is. A little add-on here that I need. There it is. This thing that I'm going to highlight is an equation, and you can tell it's an equation because it has an equal sign in it. It says this equals that. It's a statement of fact. Verify that the equation is true for x equals -3. And I want you to notice that what we've got here when we do our work in this is we don't have the equal sign anymore. We're looking at left side, we're looking at right side separately. We're trying to determine if they're equal. So on the left side, we have 2x squared minus 23x plus 5. And on the right-hand side, we have 77 minus 5x. So we want to verify if that's true or not for -3. So I put -3 in here. Of course, remembering that anytime you do a substitution, to ensure success 100% of the time, you put that thing you're substituting in its own little set of brackets. If that thing is positive, it doesn't necessarily need to be, but you'll never go wrong if you put it in brackets anyway. So we work out what this is. This is 69. This is 18. That's 79. That's 86. What is that? What does that work out to? It is 92? I was going to say 92, but for some reason I wasn't very confident there. Anybody else get 92? Okay. So now we do the right-hand side. We're going to take 77 and subtract 5 times negative 3. Well, that's 77 plus 15. That's 92 as well. So we don't really need to do anything here. We've verified that it's true. We've verified that for x equals 3, the left side and the right side are equal. This is 4 x equals negative 3. I might have said 3 a second ago, but I meant negative 3. So we've verified that it's true for a particular value of x. Is it true for x equals 12? Well, this is asking the same thing, just in a different way. We're going to put into that equation 12, 2x squared minus 23 times 12 minus 5. Whoops. Plus 5. And the other side was 77 minus 5 times x. So work this out. 5 times 12 is 60. I get 17 on the right-hand side. Can you verify you get 17 on the left-hand side? I'm pretty sure you do, if I remember correctly. Yes. Is the equation true for all values of x? This is an interesting question. I don't want to get too sidetracked into a philosophy discussion here, but you could never really, using numbers, show that it's true all the time. Because if you kept putting in, let's say we put in 1 and we discovered it was true, and you put in 2 and discovered it was true, you can never put in every number. But let's just try a different number. Let's put the number 1 in, for example. So if I use 1 at x equals 1, what's the left side and what's the right side equal to? Well, I'm not going to worry about showing my work here, because when I put in 1, that's pretty easy. I'm just going to have 77 minus 5, which is 72, I believe. So the right-hand side would be 72. When I put in 1, I'm going to have 2 minus 23 plus 5, which I believe is negative 16, but I would like your help in confirming that it is. Janessa is saying yes, so it's negative 16. So you can't, if something is true, you can't prove it's true by using numbers. But if something is not true, as soon as you use a number here to show that it's not true for one case, you're saying it's not always true. This is called a counterexample. So because we've found at least one number that makes the statement false, the answer to this question is no. It's not true for all. And I'll tell you right now, it turns out it's only true for negative 3 and for 12. Okay? Let's take a look at another equation. Warm-up number 2 has this equation. X plus 5 quantity squared plus 37 is equal to x squared plus 10x plus 62. Again, everyone, this is an equation because of the inclusion of the equal sign there. It's saying something is equal to something else. Is the equation true when x is negative 3? Well, again, we're going left side, right side. I'm going to put negative 3 in for x. I'm not going to bother rewriting the statement. It's right there on the left side. And when I put negative 3 in for x on the right side, I get that. So I have to crunch a little bit of numbers here. Negative 3 plus 5 is 2. 2 squared is 4. 4 plus 37 is 41 by my count. Good. Over here, I have 9 minus 30 plus 62. 62 minus 30 is 32. 32 plus 9 is 41. So we have verified that the left side and the right side are equal for x equals negative 3. And I don't know if you really care. It's not that big of a deal. When I did 1a at the bottom, I put left side equals right side. for x equals 3. I never actually did that over here for b. I could put left side equals right side at x equals 12. By the way, and don't, don't laugh, I had an argument about 20 years ago with somebody at Alberta Ed marking exams about this. Don't do this. This guy was kind of I don't know what his problem was. He was taking marks off because of where that equal sign was written. That there's a line through it, and he was saying the student might think that they're saying the left side is not equal to the right side. That's why, just if you're wondering, I always write it a little bit off. You just never know. Okay. All right, let's move on. Does x equals 12 make this equation true? Well, we have x plus 5, so that's 12 plus 5, quantity squared plus 37. Did I remember that right? Is that what the left side was? Okay. And the other side, I'm not going to try to remember. X squared plus 10x plus 62, x squared plus 10x plus 62, and we're putting in 12. I don't want to have to do this in my head. Is that 326? It is. I surprised myself. And watch with lightning speed how quickly I do this one. No, it's 326. I just know that they're going to be equal, okay? But do you get 326 on both sides? Okay. Is the equation true for all values of x? Well, one of the ways that we can, make our job a little bit simpler here is not to have to crunch the numbers each time, but to put in, I'm not talking about graphing anything here. I'm just using my calculator to make my job easier. I'm going to put in for y1 the left side. And for y2, I'm going to put in the right side. And I'm going to set up my table to be on ask. I'm going to double check to make sure I've entered things correctly and it looks okay. So when I go to my table, I already have some numbers in there. Oh, negative. Wow, that is a real coincidence that I have negative 3 and 12 in there, because that's from a different question that we were working on in a different class. Anyway, you can see that 5 makes it work. What about pi? Does pi make it work? Got nothing to do with trigonometry, but when I put in pi, I get the same result. So you could spend a lot of time here putting in different values for x. You could, if you wanted to, set up your table to be on automatic, start at 0 and go up by 1, and scroll around in your table and see that they appear to be equal. But again, this is almost philosophical. Do you agree that I haven't proved this? Maybe there's a number between 1 and 2 that makes it not equal, which would be really weird. But that's what math is about, is making sure that you come to conclusions that you justify. So all we can really put right now is, it appears so. I'm going to put in brackets, yes. It turns out it is true, okay, for all values of x. Do anybody know how we could prove that?
You can rearrange the left values so it equals.
Right. And we're going to be learning about proofs, trigonometric proofs, and that's exactly what we're doing. When you do a proof and you're trying to prove one thing is equal to another, you never work across the equal sign. You simply manipulate one side to turn it into the other side, or maybe manipulate the other side to turn it into the first, or maybe manipulate each of them separately to turn them into the same thing. But if we take x plus 5 quantity squared, which you probably at this level shouldn't need to write this out as x plus 5 times x plus 5, you get this when you FOIL out x plus 5 quantity squared. And if I simplify that one step further, it's not 10x squared, 10x rather. 25 plus 37 is 62, and the left side now is equal to the right side. Notice I don't write here at x equals something. It's always equal, because I didn't put in any numbers. I'm showing that the left side and the right side are really two apparently different looking things, but they are really the same. They just have different masks on, that's all. They have different appearances. All right, so now let's talk about equations and identity. An equation is a mathematical statement that equates algebraic expressions. So x plus 5 quantity squared plus 37 is an algebraic expression. X squared plus 10x plus 62 is an algebraic expression. An equation equates them, makes them equal to each other. Some equations are identities. In the warm-up, in warm-up 1, we had an equation. In warm-up 2, we had an equation. They're both equations, but only one of them was an identity. An identity is an equation that's true for all allowable values of x. And if that all permissible values bothers you, we'll talk more in detail in a minute. Just remember, an equation that is always true is an identity. Okay? There's a little wrinkle to it with the permissible values. So what are some examples of identities? Now, these are already typed out for you, but this is an identity. X plus 2 quantity squared is always equal to x squared plus 4x plus 4. Because by definition, x plus 2 squared means x plus 2 times x plus 2. This is an equation that's not always true. Is it ever true? Yeah. When x is 3, it's true, isn't it? 3 squared is 9, plus 2 is 11. When x is negative 3, it's true. But when x is 5, it's not true. So that's not an identity. It is an equation. This is an identity. Now, by definition, it's an identity because you're told that's how we define secant of a rotation angle. It's equal to the reciprocal of cosine. In other words, if you had a secant button on your calculator and you took 1 divided by cosine of any number that you were allowed to, you would get the same thing as taking secant of that number. This is an equation that's true some of the time. It happens to be true on the unit circle when you land at these two positions that correspond to pi over 3 and 5 pi over 3 for a full rotation. I want us to look at this. If you go back to Math 20-1, the left-hand side of this can be written as x plus 2, x minus 2 over x minus 2. The right-hand side of this is not in your notes, is x plus 2. Are these the same thing? Well, not really. They're not really the same thing. Because we have a non-permissible value here. And I don't know if you remember this, but when you cancel things, which you're allowed to do, and you get x plus 2, that non-permissible value here is still part of the original thing. So these are not the same. And I don't want to go too far afield in our discussion here. We have a whole lesson on this kind of thing later on in the course. But these two things will be equal anytime permissible values are the numbers we're talking about. Let me show you this on the graphing calculator. I'm going to put in, for the left side, y1, which is x squared minus 4 over x minus 2. And the right-hand side, I'm going to put in x plus 2. And I am going to set up my table to start at negative 10 and go up by 1. Okay? Don't worry about y. If I take a look at the values in the tables, I guess I didn't actually change that. if I take a look at the values of the left and the right side in the table, at -10 they're equal. When I use x equals -9, they're equal. Do you see I'm looking at the other two columns? They're always equal. 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 Wait a minute. They're not always equal. They are not always equal, but they are equal where permissible values exist. And that's why in this definition of an identity, it says an identity is an equation that's true for permissible values of x. Just because it's not true for a non-permissible value doesn't make it not an identity. And we'll have more on that later. All right, so now we kind of dive in here to finishing up the warm-up and then getting into trigonometric identities. Is that an identity? No, because there are values of x that don't make it true. Is this an identity? Yes. And we've demonstrated that it's an identity, like I said, like Miles said, just expand or simplify or rewrite the left-hand side in a different way and you turn it into the right-hand side. All right. Consider this equation. Sine of x equals cos x tan x. What are the non-permissible values of x? Well, cosine of x is defined everywhere. You can even think of a graph of cosine of x. For any value of x, it's defined. Same as sine, but tangent is not defined. Tangent of x is undefined. Is undefined at these two locations on the unit circle. And the reason for that is tangent on the unit circle is the y coordinate over the x coordinate. And this is at 0, 1, and this is at 0, -1. So when you take y over x to get the tangent of that rotation angle, you get undefined because you can't divide by 0. In other words, and by the way, the x in our equation up here is the rotation angle. The x in our equation is not the x on the unit circle. So what are the non-permissible values of x? X is not allowed to be pi over 2 plus multiples of pi. Why am I saying plus multiples of pi where the multiple is an integral multiple? Because pi and 3 pi over 2 are separated by pi radians. The top of the unit circle is pi, the bottom is 3 pi over 2. Verify that it's true for 40 degrees. We're not going to write anything here. We're just going to go to our calculator. Make sure your calculator is in degree mode. Take the sine of 40 degrees. Look at that number. Soak it in. Take the cosine of 40 degrees, close the brackets on that argument, and multiply by the tangent of 40 degrees. You get the same number. We're done. Verify that it's true for all permissible values by looking at the graphs of y equals the left side and y equals the right side. So prior to this, what we were doing in my explanation so far was we were entering the left side as y1, and we were entering the right side as y2, and we were going to our table and poking around in our table. Here we're going to look at the graphs. So I'm going to go zoom trig. Now I happen to be in degrees, but I don't care. Zoom trig. There's y equals sine of x. No, I don't see y equals cos of x tan of x. That's because it's right on top. But here's a little thing that I want to show you. If I go back to y, and for my second function, I scroll to the left of y, and I hit enter, you might remember this from Math 20, that you can shade above and below. Well, I'm not shading. I want to hit enter until I get what I call the little bouncy ball. And now I'm going to hit graph again. So here comes sine of x. And then we'll see the ball tracing out tan of x. But I want you to notice that the calculator stutters. There's a little skip in its thinking at these locations. And that's because those are locations that are non-permissible for tangent of x. That's going to be at 90 degrees and 270 degrees, and negative 90 and negative 270. So we're done with that. Is it an identity? Yes. We haven't proved it. But all reasonable people would argue that if you look at your tables and you look at the graphs, they're the same, except for those places where something is not defined. Okay, so now we're going to talk about identities on your formula sheet. These three statements were given to you as definitions before. I told you, well, cosecant of a rotation angle is defined as the reciprocal of sine. Secant of a rotation angle is defined as the reciprocal of cosine of the rotation angle, and cotangent theta is defined as 1 over tangent of theta. Well, they're identities. They're always true as long as you're allowed to use the value of theta that you're talking about. These are called quotient identities. We haven't really talked about these directly, but does anybody want to take a stab at why we know this to be true? Will?
Y over R over X over R is the same as Y over X.
Excellent. Sine of theta on the coordinate grid, whether we're talking about a unit circle or not, and I like that you included R, which includes every circle. Sine of theta is y over r. Cos of theta is x over r. This is, well, it's tan of theta, which is supposed to be y over x. If I multiply the top and the bottom of this by r, I'm left with y over x. It's not even really something we need to prove every time. It's almost an obvious statement. And then cotangent, if cotangent is the reciprocal of tangent, then it must be cosine over sine. These things that you're looking at here, these two things, as well as some other things, need to be memorable. I should be able to, I'm serious, bump into you 5 years from now and say to you, what is sine of theta over cos of theta? And you might have to think a bit, and you should go, oh, that's tan of theta. You will, by the end of this unit, and very shortly, maybe by the end of today, know that like you know 2 times 3 is 6. It's a fact, okay? Now we get the Pythagorean identities, and there are 3 of them. Does anybody want to take a stab as to why this is true? Absolutely. We can go to the unit circle here. We could do it with r, by the way, and I'll show you how that works maybe. But on the unit circle, sine of theta is y, so sine squared is y squared. Cos of theta is x, so that's x squared. But on the unit circle, x squared plus y squared equals 1 by definition. That's how we've constructed the unit circle. This one identity that I've got encircled with the green is very, very important to remember. And you will remember it. You will see it again and again and again. I actually, no word of a lie, a student came into my class one day during a trig class. He had graduated like 18 years ago, and he came in, and we were working on something, and I was really happy to see him, and I just said, hang on a second. And we were at a stage in the work, and I said, what can we do now? And he looked at the board, and he said, well, sine squared plus cos squared is 1. And he wasn't a math person. He's an electrical engineer. Well, I guess that's kind of a mathy guy, but he knew it. These other ones I don't expect you to memorize, but if you ever see something that has the number 1 and a square of a trig function, it's one of those trigonometric identities, most likely. Okay. on your formula sheet. These are not labeled, and you don't really need to know this for today, but you will later. You need to know the names of these identities. You need to know that the quotient identities are called quotient identities because they have a ratio over a ratio. The Pythagorean are Pythagorean because they're related to the unit circle and x squared plus y squared equals r squared in some way. And then the reciprocal identities are reciprocals. Okay, so verify that this is true for these angles. Let's just take our calculator, go sine of 40 degrees quantity squared plus cos of 40 degrees quantity squared. Now, it doesn't really matter whether I'm in degrees or radians because this is an identity. It doesn't matter whether it's 40 degrees or 40 radians, but I am in degrees. I hit equals, it's 1. If we do the same thing for 5 pi over 6, which is a radian measure, we would take sine of 5 pi over 6, quantity squared, plus cos of 5 pi over 6, quantity squared, it's 1. But again, as Lynette said, on the unit circle, y is sine and cos is x, and x squared plus y squared is 1. I don't think we really need to write anything down here. We know that. I've already explained it, right? All right. Prove this identity. Prove it. We know sine squared plus cos squared is 1. We have to prove this. Now, look at your pink sheet. What's the very first strategy in simplifying an expression? And let's face it, if we go on the heels of what Miles said earlier, everybody, Miles said, let's rewrite the left-hand side and make it match the right-hand side. So that's what we're going to do. The very first thing that you're given as a suggestion is to rewrite everything with sines and cosines. And that's why on the front of your formula sheet I have this meme. I don't always replace everything with sines and cosines, but when I do, it almost always works. It almost always helps. That's why it's the number one thing you want to try all of the time. Now, maybe everything already has sines and cosines, in which case you try something different. So how do we do this? Well, tangent of x is sine of x over cosine of x. How do I know that? Because I know it. Because it's a quotient identity. So tangent squared will be sine squared over cos squared. We have a whole lesson, and 2 days we're going to be spending on proofs. But in every lesson leading up to that, I squeak in the odd proof just to give us practice. When you do a proof on paper, you need to write down the name of the identity you used in rewriting things. You have to write here, quotient identity. That's part of the proof process. What do we do now? Well, I'm not going to worry about the right-hand side. Let's continue going down that list on the pink sheet. Remember to keep an eye out for familiar identities. Again, I'm working on the left side. Don't look at this, everybody, by the way, and go, oh, well, that's 1 plus tan squared. Because then you're just going back to the beginning. There's nothing we can do with the second one. The third one in that pink sheet says, thank you, try factoring. There's nothing to factor. The next one is important. Anytime you have separate terms, bring them together with a common denominator. Well, I have two fractions here. Let's bring them together to a single denominator. And those of you in my calculus class, that's what we always work towards, is a single fraction. We do it by factoring negative exponents, but here we do it by looking at a common denominator. The lowest common denominator is going to be cos squared of x. You don't need to write that down, I'm just putting it down. And that means I have to multiply the top and the bottom of this by cos squared of x. And a piece of advice here, everybody. Do that in the next step. I know it's very easy for us to just go, well, I'm going to write cos squared up here on the first line. It makes marking it difficult. And I'm not talking about you trying to make my life easier. I'm talking about a written response on your diploma exam. Show that as an additional step. Now that we have a common denominator, we can put these together and have cos squared x plus sine squared x over cos squared x. And I have a question here I want to ask at this point. And I'm going to be asking this question again and again and again throughout the next week of classes or so. And hopefully, every time I ask it, more of you will nod your head and say yes than you did previously. How many of you see that the left-hand side is equal to the right-hand side? A few. But you're not done, right? So what do we do now? If you don't see it, that's okay. Hopefully next time I ask that kind of question, you'll be in the group that says, oh yeah, I see it. What do we do here? What does that student from 18 years ago come in and look at on the board and say, oh, wait a minute, I can write what? Lynette, do you know? On the left-hand side? Anything familiar? How many of you see what's familiar? What is it? Right. Even though this is written backwards, it's 1, exactly. So I can write 1 over cos squared x, but I need to put a reason why that's the case. And the reason is, it's a Pythagorean identity. I'm just abbreviating. You probably wouldn't on a written response. Once again, this is 1. And I think at this level, you putting that in your work, putting an indication that you know that's 1, if you probably didn't write Pythagorean identity, that would be okay too. How many of you now see that the left and right sides are equal? Okay. It should be everybody, but we're still not done. You either have to rewrite the left side as secant squared of x, or rewrite the right side as 1 over cos squared of x. I'm just going to go here. This is 1 over cos squared of x. Why? Because of a reciprocal identity. And I've chosen this as the first proof in this unit because it makes use of a quotient identity, a Pythagorean identity, and a reciprocal identity. And then at the bottom of this, you write left side equals right side. Any questions with that? All right. For each of the following, simplify. I have a question for you. How many of you see that this is equal to sine squared of x? Why? This is not a proof. What do we do first? Don't always rewrite everything as sines and cosines, but most of the time it's helpful. Tangent squared is sine squared over cos squared. Look at where I write the cos squared. That's the second part of this expression. I don't write it here, everybody. I don't do this, although there's nothing mathematically wrong with that. I put it here to highlight the fact that this is, a fraction over 1, and since we have on the top things being multiplied and on the bottom things being multiplied, we can cancel. That's a Math 20 idea. Rational expressions, very important. You cancel things if they're factors. So it's equal to sine squared of x. The rest of the lesson has nothing to do with proofs. It's just simplify a particular expression. Well, write everything in terms of sines and cosines. Cosecant is 1 over sine of theta. Secant is 1 over cosine of theta. Cotangent is cosine of theta over sine of theta. I want everybody to just mentally digest this, please. Any questions in what I've done there? Okay. Multiply the top and the bottom of this by whatever you need to get rid of all of the mini troublesome denominators. This needs to go. I don't want a fraction within a fraction. This needs to go. This needs to go. So I'm going to multiply the top of this expression by sine of theta and the bottom by sine of theta. That's going to clear out my mini denominators that are sines of thetas. And I'm going to multiply the top and the bottom of this by cosine of theta. And you need to be organized in what you have left. This is multiplication all the way through. So I can cancel anything that is in a numerator and a denominator. How many of you see that this is going to be equal to secant squared of theta? Because we have 1 left on the top. The only thing surviving the top canceling is 1. And on the bottom I have a cosine of theta times a cosine of theta, which is cos squared of theta. And if you want, I can write that as secant squared of theta. And, you know, to try to, well, just to make a point here, you're only going to get better at this by doing more and more and more and more. And like anything else, the first few times you do something, it's more challenging. But as you do it more and more, it becomes easier. Well, let's write everything in terms of sines and cosines. Cosecant is the reciprocal of sine. So cosecant squared is the reciprocal of sine squared. Minus cotangent squared. Well, and you should always be looking at your formula sheet, by the way. I've made a little bit of a teaching error here. Everybody should have your formula sheet out so you can see all these identities until you get more and more familiar with them. But cotangent is cosine over sine, isn't it? I mean, tangent is sine over cos. Cosine is cos over sine. So cotan squared is cos squared over sine squared. We caught a very lucky break here. We have a common denominator. We can put these together. So I'm going to pause there. Any questions so far? How many of you see this is equal to 1? Some of you. So let's talk for a second about this identity. Anytime you see this, this is your eyeball. Anytime you see that, it's 1, right? But, and I know I'm putting a lot of pressure on you, that's not the only way to write this identity. I can write this as sine squared of theta equals 1 minus cos squared of theta. Or cos squared of theta equals 1 minus sine squared of theta. So anytime you see, I don't have room to draw my cartoony eyeball here, but anytime you see 1 minus cos squared, again, sorry, to put more weight on your shoulders, you need to go, oh, That's sine squared. So what we end up with here is sine squared of theta over sine squared of theta, which is 1. And by the way, I've mentioned this before, but I'll mention it again. You should be working top to bottom. And if you ever are forced to work left to right, don't go equals, equals, equals. If I run out of room here and I want to continue here, then write an arrow, or however you want to do it. But don't go equals, equals, equals left to right. It's a bad idea. Oh, smokes. Well, the first thing that we're suggested to do, which is to write everything as sines and cosines, is not valuable because it is already written that way. However, we have two fractions, so we're going to put these together with a common denominator. And the common denominator would have to be 1 plus cos x times sine x. There's no other way to do it. And maybe the better way to think of it is, listen, if you want to, I want to rewrite this. And I recommend that you rewrite it to give yourself a little bit of room here. If you want these to be over the same denominator, the only way that can happen is if you multiply the top and the bottom of this by sine x, and the top and the bottom of this by 1 plus cos x. Now they're both going to be over the same thing. The denominator of the combined fraction will have a sine x and a 1 plus cos x. Those of you in my Math 31 class right now will appreciate this. You do not want to expand out the bottom. Okay? For the rest of us, this is the first time, unless I had you for Math 20. By the way, everything we're doing here is rational expressions just with trig. That's all. If you had me for Math 20, we would say don't multiply out the bottom, because our hope is when you simplify the top, there's a factor on the top that cancels with a factor on the bottom. So what do we have on the top? I made a mistake here. It's not a mistake that I can't fix. I said multiply the top and the bottom by sine of x, and I forgot to write sine of x on the top. And I see very few of you writing stuff, so apparently you wrote it on the top as well. And then 1 plus cos of x. We have on the top sine x times sine x, which is sine squared of x, plus cos x times 1, which is cos x, plus cos x times cos x, which is cos squared of x. Here comes my question. How many of you see that this is equal to 1 over sine x? Here's us standing in the road. What do? You try something. Everything's already written in terms of sines and cosines. It says keep your eyes peeled for recognizable things. Well, I have this and this added together, which is 1. I'm going to rewrite it. I don't think we really need to, but some people might benefit by rewriting this top as sine squared of x. By the way, was it x in the question or was it theta? It was x. Sometimes I'll do that and I'll switch variables. If I do, I apologize. Plus cos squared of x, and then plus cos of x over sine of x, 1 plus cos of x. But this is 1. So what we have on the top is 1 plus cos of x. And on the bottom, we have sine of x times 1 plus cos of x. If I had my way in Math 20-1, we'd teach rational expressions for half the course. Factoring and rational expressions. Everything else is not nearly as important. The reason why we are allowed to do this is because 1 plus cos x is a factor of the top and a factor of the bottom. It's a factor of the top because it's written in brackets. It's a factor on the bottom because it's written in brackets multiplied by the rest. So you're left with 1 over sine x, and you could write that as cosecant of x. So on page 6 and 7 of the handout, now I may have to adjust this. It may not be 6 and 7 because I added some stuff. On 9 and 10, I believe, let's just, yeah. On 9 and 10 of the handout, those are the questions that I want you doing. I know I call this practice, but this is Math 30-1. If you don't really put in an effort here, starting now with identities, many of you will fall behind very rapidly. Trust me on this. I'm not trying to scare you or give you anxiety. I'm trying to motivate you. Okay. So tomorrow we'll go over any questions from this section, and then we're going to practice more of these together tomorrow by looking at another set of questions in your handout. Okay. So get started on that, please.